Have you ever felt that sudden invisible pushback into your seat when a bus just lurches forward? Or maybe watched a football, after a really good kick sailing through the air, but then eventually it just slows down and stops. We see this stuff all the time, but have you ever really stopped to wonder why? Like, what are the hidden rules making these things happen?
All right, let's try and unpack this today. We're doing a deep dive, yeah, a journey into how things move or don't move. We're talking about those fundamental laws,
Mm-hmm.
the ones that control everything from, I don't know, a marble rolling down a slope to a cricket fielder pulling off an amazing catch. It's actually a fascinating story how we figured this all out.
It really is. And what's great is we can follow the breadcrumbs, trace how people ask these brilliant questions over centuries. And the answers they found, well, they didn't just explain things, they completely changed how we see the universe. We're going from gut feelings, really, to Newton's incredibly elegant laws. Exactly. Think of it like a detective story. Each question is a clue, leading us from those really old ideas about why things stop all the way to Newton's big picture. So, our mission today, to make these kind of abstract rules feel real, part of a story about discovery and the wonders happening right under our noses. Okay, so for ages, like centuries, people had this really intuitive idea about motion. If you push something, it moves. Stop pushing.
It stops, yeah.
Right. Seems obvious. What was that core belief that someone like Galileo had to challenge?
Well, the common sense, based on everything people saw, was basically that rest is the natural state for objects. I mean, it makes perfect sense from daily life, doesn't it? You roll a ball, it stops. A cart needs constant pulling or pushing. It just seemed obvious that things preferred to be still.
Right. Everyone knew that. It was just how things worked. And then Galilei comes along, a real game changer. And he asks, hang on, what if we're looking at this completely wrong?
Precisely. He wasn't just looking at the stars. He was rethinking motion right here on Earth. He did these amazing thought experiments. Picture this. An ideal setup, totally smooth, a double inclined plane. He imagined releasing a marble from one side. It rolls down, naturally, then up the other side, almost to the same height.
Okay, yeah, I can picture that.
Now, here's the genius bit. What if you make that second slope less steep? The marble rolls further, right? Keep making it less steep until it's completely flat, horizontal. In his perfect, frictionless world, Galileo realized that marble wouldn't stop. It would just keep rolling forever, trying to get back to its starting height.
Whoa, okay, hold on. Forever. That's huge. So it completely flips it. It's not about what makes things stop. It's about what makes them change their motion. Is that it?
That's the core insight exactly. It implies that moving steadily, uniform motion, constant speed, in a straight line that can be just as natural as being at rest.
But hang on, if things can just keep moving, why does my football always stop then? What am I missing? There must be something.
The catch is friction and air resistance. Galileo's point was that you need an unbalanced force, an external push or pull, to actually change how something is moving. But you don't need a force to keep it moving uniformly if you could get rid of those pesky things like friction. Your football stops because friction with the grass and air resistance are acting on it. They're unbalanced forces. Take those away, ideally. It keeps going. This was a revolutionary idea. Like saying the Earth moves. It shook the foundations.
And Galileo wasn't just dreaming this up, right? He was very hands-on. Didn't he do work earlier, like with the little balance,
Right.
measuring things precisely?
Absolutely. That practical side was key. The little balance was an ingenious device he made very early on to measure the density of materials very accurately. It shows his commitment to careful observation and measurement, which really underpinned all his later breakthroughs. He wasn't just guessing.
Okay, so we've talked about these big ideas. Let's bring it back down to earth. Literally, how do we actually feel or see force day to day? It's not just a formula, is it?
Not at all. We experience it directly. It's that muscular effort, isn't it? A push, a pull, sometimes even a hit or a twist. Pushing a door, kicking a ball, pulling a heavy bag, that's force in action. We feel it.
And what do these forces actually do? What are the results when we apply a push or a pull?
Well, force is basically the agent of change for motion. It can speed an object up, or it can slow it down so it changes the magnitude of velocity. It can also change the direction of movement. Think about steering a bike or a car. And sometimes, if the force is strong enough, it can actually change the object's shape or size, like squishing a sponge.
Right, but it doesn't make it invisible, thankfully.
No, definitely not that.
So this leads to a key point. When does something just keep cruising along steadily, and when does its motion actually change? Like a car on the motorway versus one starting from a traffic light.
That's all about balanced versus unbalanced forces. An object keeps its uniform velocity, same speed, same direction, when all the forces acting on it cancel each other out. The net force is zero. Think about trying to push a really heavy wardrobe. If you push but it doesn't move, your push is being balanced out by friction, right?
Right. Happens all the time.
But the second your push becomes greater than the friction, the forces become unbalanced. That's when things change. The wardrobe starts moving, the car accelerates away from the lights, or if a car is cruising and you apply the brakes, that's an unbalanced force slowing it down. Uniform motion continues unless an unbalanced force messes with it.
Okay, so building on Galileo's amazing ideas, Newton came along and gave a name to this resistance to change we've been circling around, this sort of stubborn quality objects have. What's that called?
That concept is inertia. It's defined as the natural tendency of objects that are left alone undisturbed to either stay put if they're at rest or to keep moving exactly as they are, same speed, same direction. It really is like a fundamental stubbornness in matter. It resists changes to its motion.
Okay, inertia is a tendency. But how do we measure it? Can we put a number on how stubborn, how inertial an object is?
Yes, absolutely.
Yeah.
The way we measure inertia quantitatively is by its mass. More mass means more inertia. It's harder to get moving and harder to stop once it is moving.
Oh.
Okay, think about it. A huge train has vastly more inertia than a bicycle. It takes a massive effort to start it or stop it, or even a simple stone compared to a rubber ball of the same size. The stone has more mass, so it has more inertia. It resists being thrown or stopped more strongly. Mass is the measure of inertia.
And this whole idea, this inertia, this resistance, it's so fundamental, it became Newton's first law of motion, didn't it?
Indeed. Newton's first law, sometimes just called the law of inertia, basically codifies this. It states, an object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction, unless acted upon by an unbalanced force. It formalizes Galileo's insight and makes it a cornerstone of physics. It tells us the default state isn't necessarily rest, it's constant velocity. Change requires a cause, an external unbalanced force.
You know, when you put it like that, it explains so many little everyday things, those aha moments. Like I remember being on a bus that started suddenly and whoosh, I felt thrown backwards. That's inertia, right?
That's it, exactly.
Yeah.
Your body, because of its inertia, wants to stay put, stay at rest. But the bus moves forward underneath you, so relative to the bus, you feel like you're thrown backward. Or think about beating a dusty carpet with a stick. Why does the dust come out?
Never thought about it that way.
The stick forces the carpet to move quickly. But the dust particles, having inertia, tend to stay where they were, just for an instant. So the carpet moves away from the dust and the dust falls out. It's inertia keeping the dust momentarily at rest. A great little demo.
Okay, so objects resist change because of inertia measured by mass. But how do we quantify that change itself? And what about the impact a moving object can have? It's not just about mass, is it?
No, you're right. It's more than just mass. That's where momentum comes in. It's the concept that captures well, you used the word oomph earlier, and that's not bad. Momentum, we use the symbol P, is basically the measure of motion quantity. It's the product of an object's mass and its velocity v. So P equals mv.
P equals mv. Okay.
And the unit just reflects that. Kilograms times meters per second. Kilojms, that tells you how much mass in motion something possesses.
And that really makes sense. Like a big truck parked is no problem. Dangerous. Why?
Because the impact an object can deliver depends crucially on both its mass and its velocity, which is exactly what momentum captures. The truck has huge mass, so even a small velocity gives it significant momentum and thus a large potential impact. On the flip side, a tiny bullet has very little mass, but its incredibly high velocity gives it huge momentum, making it dangerous. Momentum is key to understanding impact.
Right. So now, the big one, Newton's second law. How does this connect the force we apply to this idea of momentum, this oomph?
The second law gives us the precise relationship. It states that the rate at which an object's momentum changes is directly proportional to the unbalanced force applied to it, and that change happens in the direction of the force. Basically, it tells you how much force you need to change the momentum by a certain amount in a certain time.
Okay.
And this leads directly to maybe the most famous equation in physics, F(a). Force equals mass times acceleration, because acceleration is the rate of change of velocity, and momentum involves velocity and mass. So force causes mass to accelerate.
F(a), got it. And the unit of force is the Newton.
Yes, the Newton N,
Yeah.
which is defined as the force needed to give a 1 kilogram mass an acceleration of 1 meter per second squared, kg is Hone. It neatly ties force, mass, and acceleration together.
And this law isn't just theory, it's used everywhere, like in sports cricket, for example. Why do fielders pull their hands back when catching a fastball? I always wondered about that, Sting.
Ah, perfect practical application. By pulling their hands back while catching the ball, the fielder increases the time it takes for the ball's momentum to drop to zero. Since the change in momentum is fixed, the ball stops, increasing the time means the rate of change of momentum is lower. And because force is equal to the rate of change of momentum, FMA essentially, a lower rate means less force is exerted on the fielder's hands, less sting, less chance of dropping it. It's smart physics.
That makes so much sense. Okay, another one. Pushing a car with a dead battery. Why is it better to give a steady, continuous push rather than just one big, sudden shove?
Same principle, really the second law in action again. A continuous push, even if not super strong, is applied over a longer time. This allows that force to gradually change the car's momentum over that extended duration, building up its speed. A sudden hard push, even if momentarily stronger, acts for such a short time that it doesn't change the momentum significantly. The car's inertia resists that brief impulse. Time is crucial for changing momentum effectively.
Right, the duration matters. One last clarification on this law. Sometimes in calculations, say for braking, you see force as a negative number. What does that negative sign tell us?
The negative sign is simply about direction. It indicates that the force is acting in the opposite direction to the object's motion, or whatever direction we've defined as positive. So if a car is moving forward, positive direction, the braking force acts backward to slow it down, hence it's represented as negative. It keeps track of which way things are pushing or pulling.
Okay, moving on. Now for something really interesting, this idea that forces never seem to act alone. They always come in pairs. What's Newton's third law all about?
Yes, this is Newton's third law. It states that for every action, there is an equal and opposite reaction. More formally, whenever one object exerts a force on a second object, the second object instantaneously exerts a force back on the first object. This force is equal in magnitude and opposite in direction. Forces always come in pairs.
Equal and opposite. Now, this is where people, including me, sometimes get confused. If the forces are equal and opposite, why don't they just cancel out? Why does anything ever move?
That is the absolute key point and a common misunderstanding. The reason they don't cancel out is that the action force and the reaction force always act on different objects.
Different objects.
Exactly. They can't cancel because they aren't applied to the same thing. When you push a wall, action hand pushes wall, the wall pushes back on your hand, reaction wall pushes hand. One force is on the wall, the other's on your hand. They don't negate each other's effects on the individual objects.
Okay, that clarifies it. But if the forces are equal in size, why don't the two objects always accelerate equally? Like if I kick a football, the ball goes flying, but my foot barely moves back.
Because of Newton's second law again, ESMA. The forces are equal in magnitude, yes, but they are acting on objects that might have very different masses. The force your foot exerts on the ball, low mass, causes a large acceleration, ball flies. The equal force the ball exerts back on your foot, attached to your leg, much larger mass, causes a much smaller acceleration. Equal force, different masses, therefore different accelerations. Got it. Okay, let's nail this down with a couple more clear examples.
Sure. Think about the football kick again. Action. Foot exerts force, ball forward. Reaction. Ball exerts equal force on foot, backward. The ball accelerates a lot, your foot-leg combination accelerates very little. Or consider firing a gun. Action. The gun exerts a strong forward force on the bullet. Reaction. The bullet exerts an equal backward force on the gun.
Ah, the recoil.
Exactly, that's the recoil. The bullet, tiny mass, gets a huge forward acceleration. The gun, much larger mass, gets a smaller backward acceleration, which is the kick you feel. Action-reaction pairs, always there. Wow. What a journey we've taken. Seriously, from those ancient ideas of things just wanting to stop, through Galileo's amazing thought experiments about ideal motion, all the way to Newton's three laws, inertia, FMA, action-reaction. It really feels like we've uncovered the operating system of the physical world, you know?
It really does feel that way sometimes. Yeah. We've seen the hidden physics behind why dust flies off a carpet, how a cricketer makes a safe catch, the kick of a gun. These aren't just equations in a book. They are fundamental rules that govern absolutely everything that moves or stays still in the universe. They're always at play.
So what's the takeaway for you listening right now? It means that if you understand these core ideas, inertia, force, momentum, these action-reaction pairs, you literally start to see the world differently. You can predict things, understand why things happen the way they do. Simple, everyday actions suddenly have this deeper layer of meaning.
Which maybe leads to a final thought for you to carry away. The next time you push open a heavy door, or maybe jump up in the air, or even just feel your seatbelt lock during a sudden stop, Trying to think about it. Can you spot the forces? Can you feel the inertia? Can you imagine the action-reaction pairs? How many examples of Newton's laws can you find just going about your day?
Keep looking, keep asking why, and keep exploring this amazing moving world around us.